Hi, everybody. So here we are with lecture 3. We're going to talk about universal properties today. So this is the third lecture in our category theory crash course with quantum formalism. So I've kind of alluded to this a few times throughout the lecture so far, especially in terms of things like initial objects in a category and terminal objects in a category. These are elements of some category that are sort of determined by some property, and this property sort of uniquely characterizes them. These are uniquely characterized by property. And I'm going to go over this quote right here in just a second. But when I mean uniquely characterized by some property, I mean exactly that, in the sense that if any other object satisfies that property, it is isomorphic to my object. So for example, for the initial object in the category of sets, I think I wrote it's just set before. The category of sets, the initial object, empty set, is in the category of sets. So I should say the empty set. Is quote unquote the initial object. So that, and by initial object in this case, it means that it's a subset of every set. That's one way you can determine it. For any set X. Likewise, we saw that the terminal object it admits a map from any set. So the terminal object in this case was a singleton set. The singleton set. Which I sometimes denote by just like an asterisk or like a bullet. So it's a set containing only one element. Any set containing only one element is the terminal object. Terminal in the category of sets. So we saw here that there are many different kinds of singleton sets. And I think the example I gave in the first lecture was the set containing just the letter A versus the set containing the word chair. This was a silly example, but they both satisfy the same property. It's a set containing only one element, and the property that it really is important is that for any set, there exists a unique function from X to that set. And so this function in this case, you just send X to the only element of that set. You send it to asterisk. So whether it be A or whether you send X to chair, it doesn't really matter. And we saw that this sort of determines the set containing only one element up to isomorphism, up to bijection of sets. So we're going to abstract this a little bit. I claim that this is nothing new to most of you. Maybe you haven't seen it in this language. You haven't seen it isolated in this case, but you've seen many instances of this kind of thing. Just like many of you have seen the empty set or a set containing only one element, just maybe not phrased in this particular way. So now back to this quote. A universal property is a property that characterizes up to isomorphism the result of some construction. So some kind of construction, some process, or some property uniquely characterizes some object of a category. Maybe I should say uniquely characterizes. So for our example, right here, for the initial object, the empty set in the category of sets, the property I'm trying to characterize is a subset of every set. is a subset of every set. Or alternatively, you can think about it as, for any set X, there's a unique map from the empty set into that set X. So here, I'm going to say these are equivalent. And here, the property we're trying to characterize is that admits a map from any set. Which was phrased this way. These are sort of like dual properties here. There are many other instances, so I'll go over a couple of examples of these really quick. Some of these I will not kind of go into too much detail with. Some of them I'll explain in this lecture, and some of them I'll just allude to, making you guys search them for homework. Again, I think I've said it a few times now, the utility of category theory is recognize it in your own field. It is a tool. It's an organizing tool. So recognizing when you're seeing a categorical property at work or a categorical kind of idea is really powerful. It gives you access to this consolidating, abstracting language. All right, so what do I mean by this? So maybe some other examples. Let's say I could do, free groups or free vector spaces. Free vector spaces. Quotient groups. Quotient vector spaces. Same thing with quotient topological spaces. Kernels, or maybe I'll write, kernels or co-kernels of group homomorphisms. All right, I'll abbreviate that by HOMs. Same thing as, co-kernels of linear maps between vector spaces. And I'll abbreviate that as, V spaces. I could do, let's see, direct products or direct sums. Of vector spaces or modules or topological spaces. I could do, let's say, completion of a metric space. For example, you could say, the reals from Q, the rationals, or even the p-adics, if you've seen those. These are p-adics. Actually, I think that's the wrong word. I think I should do ZP. I could do, let's say, tensor products. Fiber products, or pullback diagrams. These are sometimes called pullbacks. Likewise, you can have something called a fiber coproduct or a push out. There are many, many things. The list kind of keeps going on. These are ubiquitous. Oops, I can't even spell math. Once you kind of recognize the framework or the language, you'll start seeing them everywhere. They're not even just in like traditionally categorical things like abstract algebra or algebraic geometry or something like that. You can see these in analysis. You can see them in topology, linear algebra, anything. They come up everywhere. These are an organizational tool. So we've seen, if I'm doing, let's say, free groups or free vector spaces, is the property that defines these things the same? Is it the same kind of diagram, just in a different category? Likewise, as an exercise, what I'm going to give you guys later is showing that this is actually the same property, the property of being a quotient object. It just happens to be in different categories. The diagram you draw for a quotient group is the same one you draw for a quotient vector space, which is the same thing you draw for a quotient topological space. The context just happens to be different. Likewise, co-kernels, same thing. Groups, topological, groups, vector spaces, all the same. Products, co-products, whatever that means. These are all the same property. They just happen to be in different contexts. That's the power of this organizational tool. So we'll see a couple of these examples. Some of them I will kind of elucidate now. Some of them I'll kind of hint at as exercises, and some I will just ask you to find, and we can talk about them in the problem session on Sunday. I encourage you to really find more. So maybe this is your exercise 1, the most important one. Find more. We don't really know what this is, right? We only have a very loose definition and, a very loose example. Right now we have just only seen the empty set and singleton sets. And I've told you that these are all examples. But you can kind of get a feel for some of these after the following examples. So my favorite one to start with is the kernel of a group homomorphism. Example 1. I'll just write example. The kernel of group homomorphism. So this context means I've got two groups, G and H. I've got some homomorphism between them. So this is a group hom. So recall, maybe really quickly what that means. It's so like phi is a function between the underlying sets. Of G and H. So it's like a set function, and it preserves the product structure in G and H. Such that, so if I have two elements G1 times G2, so this is the group product in group operation in G. This is output turns into the group structure or group action in H. This is for all G1, G2 in big G, you have this. So that's what a group homomorphism is. I know that a lot of you have taken the group theory crash course with concept of formalism, or maybe you've seen it before in your own classes. This is just a refresher. If you don't like this thing, or this is less familiar to you, you can just take something like, I've got a vector space V and a vector space W, and I've got a linear function between them. So this is like, K linear over for some field K of vector spaces over the field K. Cool. So the kernel of phi is the following subgroup. So the kernel of phi, which I'll write as ker phi, is so it's a normal subgroup. That's not super important for us right now, but it's a nice thing to know. Normal subgroup of G defined by, so we write it as a subset. So it's exactly all the things in G that are killed off by the map phi. And by that I mean it's sent to the identity element in H. So for example, maybe I'll do, if I have the group of integers under addition, and I have the group of integers mod n, right, this is Q, then, so this is the map that sends, an element m to the coset m plus nz. This has kernel equal to the subset of integers that are multiples of n. Multiples of the integer n. Right, so this is cool. This is how we usually see it. So this is, the usual definition. But I'm going to think about this thing slightly differently. I'm going to define it sort of in relation to other subgroups of G. What I'm going to say is that the kernel phi, the kernel of phi is the largest subgroup, maybe I'll say normal, of G, such that or that is killed off by phi. I'm going to say annihilated by phi. So the way I'll kind of write that is, if, let's say, if I write G right here, G, H, and phi, and if I write kernel phi as a subgroup, there's a natural inclusion of this subgroup into G. So I'll write as I sub phi. So by killed off by phi, I mean, if I compose these two maps, make the associated commutative diagram, this should be equal to 0. So this gives me a kind of diagram. This is a diagram going on. A commutative diagram. So what I want to investigate now is this sort of defining property. So maybe G has many subsets or many subgroups that are killed off or annihilated by phi. The sort of unique property here, the thing that's characterizing it, is the fact that it's the largest such subgroup. This is the important thing, that it's the largest. So let's try to rephrase that. Basically, another way of thinking about this, I'll do first the kind of thing in words and I'll write the associated diagram, is this means if K is any other subgroup, I'll write it like, I think we usually write normal subgroups as this, is any other normal subgroup such that if I restrict phi to K, it's identically 0. So maybe if I write I sub K as the inclusion into G, i.e. phi composed with I sub K equals 0, then there's an inclusion. then K is in fact a subset or a subgroup of the kernel. So if K is any other subgroup that satisfies sort of this property right here, then in fact K is a subset or a subgroup of the kernel. So I'm going to write this in terms of diagrams now. So what I'm going to do is say here I've got my G, H, phi, I sub k, k, and I know that this composition is equal to 0. So this is kind of the setup. This is what this part is saying. So I'll get rid of some of this here. This part is kind of just identifying this property. That's what this diagram is doing. Maybe if I want to kind of be a little more explicit, I'll write it's a subgroup. I'll add like a little hook there to mean it's a subset and also a group. So K is a subset of G, and it's killed off by phi. Okay. What this is saying is that there's actually, if this is true, that implies that there exists a unique morphism from K to the kernel. Another unique inclusion, making all these diagrams commute. So the way I'd phrase this is like, instead of having the K right here, really what the diagram should look like is this. So I'm going to put my kernel right here. This is composition 0. K is some other object that satisfies this property. So it's got some kind of map into G. It's got some other map, such that if I compose phi with I sub k, I get 0. This property right here is saying that I get some unique map. There's just a unique map between these two. Okay, this seems kind of unnecessary a little bit. I feel like the first pass, maybe this is a little bit cool to phrase things this way, but it's not groundbreaking, right? This just seems like a different perspective. So let's turn it back and kind of recontextualize it in terms of these guys, my initial objects and terminal objects. Okay. So what I'm going to do is take this kind of diagram over here, and I'm going to create a category. So we're going to define a category. A category of diagrams. Of the form, I've got a morphism from G to H, phi goes there, I've got some group K going here, admitting a morphism I sub k, such that this composition is equal to 0. So these are my objects, consisting of objects of this form. For some group K, with morphism K going from to G, and composition of I should get getting ahead of myself. Morphisms between diagrams are exactly of this form. So if I have two such objects, so a morphism of such diagrams is given by, so here I'm going to need a morphism. Let's say if I have one thing in this form, K1, I1, 0, and I've got this, I'll call this I2. And so if, say I want to define a morphism between these two things, so I'll call that psi. So what this actually means is that it's given by the following. So given by a group HOM psi from K1 to K2, such that everything commutes, such that the following diagram commutes. So if I have my G to H as usual, got my I sub 1, K1, or how do I want to write this? G goes here. I'll put K2 right here. K1 goes right here. Here's my map psi. Here's I1. Here's I2. Oop, geez, I had that backwards. I1, I2. And they both have a map that is 0 going to H. The following diagram commutes. Cool. So this seems like kind of unnecessary abstraction a little bit right now, but the punchline is the following. So one thing I need to do is maybe exercise 2 is to check this is actually a category. Exercise 2. Check this is actually a category. Cool. Okay. So the punchline is now the following. So the diagram I gave for the kernel, kernel of phi, I called this one I sub phi to make it look special. This diagram is a terminal object in the category above. And I'll call this category, I don't know, I'll just call this groups over phi. I don't know. Doesn't really matter. We'll call this category D. I'll come up with a nice name for it later. Is the terminal object. In the category of diagrams, D. This is the punchline. I've turned this completely practical thing, being a kernel of a group homomorphism or of a linear map, it's going to be the exact same diagram, into a categorical property. It's in fact one we've already seen, being a terminal object in some category. So that's kind of nice. This kind of property we had right here, that there exists a unique morphism from K into the kernel such that all the relevant diagrams commute, is exactly the same thing as being a terminal object in the category of diagrams that are killed off by the map phi. So there's one kind of issue here, I'm hiding under the rug, which I'll turn into an exercise. Exercise 3. why didn't this, why does this all work? So one thing I noticed was, one detail I kind of left out is in my group homomorphisms from K to G, I didn't really require that K was a normal subgroup of G. Is a subgroup or a normal subgroup. I just required that it was a some group admitting a morphism into G that is killed off by phi. Why is that okay? Why does this work? And, the thing that, so the question is, why does this still work? And the hint is to think about the image of this morphism. Image of the map phi. So in particular, you can think, what's the difference between, if I got the map K here, is there anything different between this diagram where I have K, 0, versus G going to H, and the image, which I'll write as just I am of phi. Can I even tell the difference between those two things with this kind of setup? Does it really matter? And it turns out it doesn't really matter here. Maybe there's a second part. How do you define maybe it should be exercise like 3 A or part 2, say this is part 1, this is part 2. Can you find a universal property defining the image of phi? Maybe say if any, or if it exists. So the universal property defining the image of the group homomorphism phi. This is a good, learning thing. So this is exercise 3, part 1 and part 2. Cool. Likewise, doing the exact same setup. So similarly, I mentioned co-kernels before. For co-kernels, so if we have G to H, again, the co-kernel of phi, which we usually abbreviate as co-cur of phi, is defined to be the quotient group of H by the image. So one could say it's the smallest quotient group of H that is killed off by phi. So I'll write that here. Co-cur phi is the smallest quotient group of H such that I do first going from G to H via phi, and then for H to the co-kernel, I'll call this J sub phi, this composition is equal to 0. So again, this map J sub phi is just exactly the canonical quotient map from H mod the image. So you can form another similar category of diagrams. You can do like, all things of this form where L is some quotient group. Such that this composition is 0. You can form a cat of diagrams. In the exact analogous way as we did for the kernel. And in this category, the co-kernel is the initial object. So I'll call this, I call this other one over here, like, where was it? I'll call this D sub phi. And I'll call this one D sup phi. So co-kernel of phi, or rather this diagram here, this is the initial object in that category. In the category D sup phi. The category of diagrams representing the kernel, or the co-kernel, rather. So I'll go over a couple more examples. And to kind of give you an idea that it really all boils down to setting up your example, your property, as an initial or terminal object in some suitable category of diagrams. Each one of these things we gave right here is of that form. So maybe I'll do, let's see. I'll do one more big example from topology, and then I will, let you go for the day, or at night, or wherever you are. Again, this is meant to be like a really example-heavy lecture. Next class, where we talk about something called limits and co-limits, we'll talk more about what I mean by a category of diagrams. So we'll kind of axiomatize this kind of construction, a category of diagrams, next time. So we'll kind of rigorously go through what it means to have a category of diagrams and this sort of construction. This is in the idea of limits and co-limits. All right, so from topology, we have the following kind of cool thing. So it's an example from topology. So if you've seen some topology before, I'm not going to go over the definitions of topological spaces or continuous functions, but we can form a category. I mentioned this, I think, in the first lecture. Form category. I'll call this top of topological spaces and continuous functions between them. And continuous functions. Cool. So let's go over a very simple example, the product of two topological spaces. So let x1 and x2 be topological spaces. I'll abbreviate that as top as P. We can form the product space x1 Cartesian product x2 as follows. So as a set, this is just the Cartesian product. As a set, this is Cartesian product. Cartesian product. And the topology is given as follows. So with this product space, there's two canonical maps. So I can define two functions as sets onto each of the factors here. I'll call this one P2 and I'll call this one P1. So P1 takes an element x1 comma x2 and it just returns x1. Likewise, P2 returns the second factor. So these are both perfectly valid functions. We're going to use these to define a topology. So the topology on x1 cross x2 is the coarsest topology for which P1 and P2 are continuous. So this is we're using these set theoretic functions to define a topology sort of relationally. So this means particularly, if U is a subset of x1, then P1 inverse of U is open in x1 cross x2. Maybe I'll write this as x sub I, U sub I. Is open. This is a way of defining the topology. So this is kind of boring on just a product of two spaces, but it gets really interesting when you have like larger products. Okay. So how does this kind of help us? What am I doing here? Another way of phrasing this thing is the following. So this is already kind of a relational thing. We know that this is coarse topology for which is kind of a sort of a ringer for universal property in my head. Whenever I see biggest subgroup, smallest subgroup, best possible thing, least efficient thing, smallest, whatever, I know to think about in terms of universal properties. So maybe I'll write this as kind of a note. Universal properties identify objects that are sort of like the best. best or maybe most optimal. At that property. So whenever you see, e.g., biggest object, such that smallest, finest, coarsest, e.g., etc. So, for example, there are many topologies on this thing that make these maps continuous. For example, I can give this thing the discrete topology. The discrete topology makes these maps continuous as well. So the discrete topology, if you don't remember, is the topology on which every subset is open. So, while this does satisfy the same property, it's sort of not optimal in some sense. It gives us too much information to be useful. If everything is open, we don't really learn anything about the structure of x1 and x2 in terms of x1 and x2. Right? If everything is open in here, what does it have to do with the subsets or the topologies on x1 and x2? We don't really learn anything. So we want to add as few subsets as possible that make these maps continuous. I can also phrase it in terms of, instead of talking about just x1 and x2, I can define it in another way. So this thing kind of explicitly gives you the set. This sort of explicitly gives you right. I said it's the product space is, the Cartesian product as an underlying set, and the topology is given like this. I'm going to define it in terms of, an initial object or terminal object in a suitable category, like I did before. So what I'm going to say is I'm going to look at the following. So I'm going to look at the category, define a category of topological spaces, or of diagrams of topological spaces. So they'll be of the form like, here's some topological space Y, and here's admitting a map to x1 and x2. We'll call f1 and f2. This is some topological space. And the fi are continuous. These are both continuous. Cool. Then, again, just like before, I can turn this thing into a category, and the morphisms look like this. So I'd have, y and z, so I'd have some functions, say g, between y and z that make these maps commute. So if this is, let's call this, say, phi, or psi. So this is continuous such that the diagram commutes. Then the diagram of this form, x2, p1, p2, is the terminal object in this category. So in particular, this really reframes it as it's not just it isn't just the space itself, x1 cross x2, that's important. It's that space together with the projection maps P1 and P2. So the whole diagram is important. The whole diagram is important. Not just the space itself. So the way this usually kind of comes up, sometimes you'll see this maybe like in the book Munkris topology. It means that if I have any topological space Y admitting maps F1 and F2 to X1 and X2, there exists a unique map, which we'll call F, into the product. Makes the following diagram commute. So F satisfies, if I compose it with any of the projections, P sub I get F sub I. Okay. So I gave you a couple exercises. One thing I'm going to give you right now to finish, I think, is exercise 4. What happens if I look at the initial object in this category? If I reverse the arrows everywhere, if I look at the opposite category and look at its initial object, or terminal object, I should say. Wow. If I reverse things, first some arrows. So now my diagrams look like this. So I've got x1 and x2 here, and I've got maps into some space Z, which I'll call, now I'll call these G2 and G1. So if I have some other space, let's say it Y. Oops. With F2, F1, and morphisms look like this. What is special about this category? What object am I defining? I'm looking at this category of diagrams. Does this thing have a terminal object or initial object? And if so, what does it represent? What kind of classical object is it? Okay, and the last one, exercise 5. So there's a similarity between quotient vector spaces, quotient groups, and quotient topological spaces. These all seem similar. So what I want you to do is write down the corresponding universal property that describes these objects and see how they compare. Are they similar? Are they the exact same property, just different categories in which you're kind of computing them? So draw, or maybe identify the universal property. Find the category of diagrams. And finally, compute the initial object or terminal object and see how they're similar. All right. I'll see you next week.